All right, what we left off on Friday doing was firing an object horizontally like that. And when we did that, we took a look at what the path was. We had a half parabola for our path. And essentially we said that when we orient our velocity this way, we called it Vx because it is exclusively in this direction. And then we said that it has no vertical velocity, at least to start out. That changes once gravity gets a hold of it. And what we did was we analyzed it using kinematic equations that we're already used to analyzing it. Now, because the acceleration was 0, we said that delta x is simply vx times t. There's no acceleration in the x direction. And then for the y direction, we said that delta y, we'll use our same equation, but now we've read a subscript of y for our vertical velocities, and we're going to want to separate them out each and every time. So you have vyit plus 1/2 negative gt squared. We also have vyf equals vyi plus negative g times t. And the last one is vyf squared equals vyi squared plus 2 negative g delta y. And we use those to analyze the equation. And what we did was, we separated out the x direction from the y direction. We're going to look at a little bit of a different problem today, something that's fired off at an angle. So if we're going to look at the cannon's now not going to be oriented this way from an elevated position. It's going to be oriented like this. And what ends up happening is that if I throw my ball at an angle, release it with a velocity directed somewhere like that, you're going to see that the shape of that is still parabolic. Although now what you're seeing is you're going to see the full parabola as opposed to just a half parabola. So we have a different problem at hand, and the problem on both of your sheets involves a cannon that fires something at an initial velocity of 30 meters per second, and the angle is 40 degrees. So what ends up happening is that our initial velocity, Vi, is 30, and it's at an angle. Now, here's the problem with this. We cannot take this number and stick it into these formulas. These formulas are for components only, horizontal velocities and vertical velocities. So what we're going to have to do to this velocity here is we're going to have to break it down into the vectors that would make it up. So I need to break it down into a horizontal velocity and a vertical velocity. And I do that by forming a right triangle from this vector here. So it's going to be broken down into a velocity that we'll call Vx. And remember, Vx never changes. And its starting y velocity, Vyi. So basically, we have a triangle here where the hypotenuse is 30. We know the angle, and we want to find the other two sides here. So essentially, this is going to be O, and this is going to be A, and this is 40 degrees. So if we're doing SOHCAHTOA here, we can get into components. What we know is that sine theta equals O over H. So if I want this Vyi, I'm going to have to use sine. And essentially, if we're looking at it, we're going to say that, okay, sine 40 would equal O over the hypotenuse of 30. Now what you're going to find is that if we just multiply both sides by 30, we'll get our O or our Vyi. So basically, all we have to do is take that initial speed and multiply by 30 sine 40, and we will get the numerical value for our vertical velocity, which ends up being 19.28 meters per second. That is Vyi. We do the same thing for the x direction. It's just that we're going to have to use cosine there. So if I was doing cosine theta equals A over H, it'd be cosine 40 equals A over 25. Now, if I multiply both sides by 25, I would get A. So essentially, when you're doing Vx here, it's just going to be your 30 times cosine of 40, which ends up being 22.98 meters per second. So now we know how fast it's moving to the right and how fast it's moving up at the time it's fired. And so those are our starting conditions. And what you're always going to want to do is kind of make a table to see what you have and keep track of everything. So we'll do that. In fact, some people like to do it with the x direction and the y direction separately. So in the x direction, let me actually make that look like a y. We have delta x, we have vx and t. And then for the y direction, we would have delta y, vyi, vyf. You don't have to write t again because that appears in both formulas. And then we know what g is, right? So negative g is negative 9.81 meters per second squared. And we know our values here for vx. That's 22.98. And vyi is 19.28. Now what you're going to find is that we always have to do the x direction different from the y direction. And ultimately, we want to figure out, the questions posed to us on the first sheet is, well, if this thing is going to follow a path like this and return back down to the ground at a much farther location, how far away is that? That's something I would call delta x. That is the horizontal change in position right there. And in order to figure that out, we need to know Vx and we need to know T to use that to put it into that formula. We don't know T, that's the problem here. So we have to do the Y direction first. And if we're going to do the Y direction first, we need 3 out of the 5 to get T. I got 1 and I got 2 out of 5. Vyf, the velocity that it strikes the ground with, I have no idea what it is. T, I don't know what that is either. I'm trying to solve for it. This isn't explicitly told to you, but if you look at the initial and final points, it starts at the ground and it ends at the ground, which tells you that delta y for that whole trip is 0. So we actually do know 3 out of 5. And so if I go into this formula here, now remember there's no wrong formulas here. You can actually use all the formulas and still arrive at the same answer that I'm going to. But if I use this one, it's probably going to get it to me in one step here. So I'm going to write delta y, vyit, 1/2 negative g t squared. And let's put in our values of 0, 19.28. There's a t there, 1/2 negative 9.81, and t squared. We'll be able to solve this. In fact, because one of the sides is 0, we can divide both sides by t, and you'll be able to solve for t pretty easily here. And when I solved for t, I got 3.93 seconds. So that's kind of going to be something that we want to fill in here. T is 3.93 seconds. And now we can easily get delta x, because for the x direction, if you got 2 out of 3, you can get the third. And that's always going to be the easiest direction. Delta x equals Vx times t. And that would be 22.98 times 3.93. Multiply that out, and I think we're going to get something like 90.3 meters if I've done it correctly. So always going to be x direction separate from the y direction. You may have to do one before the other depending upon the information that you're given. And that's basically how we want to approach a range and a time of flight for an angled projectile. In the other video, I'm going to show you how we actually take a look at this same problem, but we go, how high does it go?